Hi guys, Buildzoid here, and today we're going to be taking a look at this here Maximus 11 gene, which as you can probably tell is not a Maximus 11 gene you can buy in a store. So basically this thing exists because obviously the Probinator just I love modding things, right? I love modding GPUs. I love modding, well, motherboards, everything. If it's modified, if I can mod it, I'll try to mod it. And with the Probinator, I finally have a great, an excuse to add capacitors to motherboards because now, instead of trying to get the CPU to actually overclock better, which is kind of hard to reliably quantify that there is an improvement, I can just look at the oscilloscope and see if the minimums are better. Right? Like, I can just measure if there is an improvement. And so, as a result of that, I've absolutely gone to town on this Maximus 11 gene. And I've done quite a lot of things to it. So the most obvious and kind of difficult modification is obviously these inductors. So these inductors right here are off of a Vega 56 that was dead. That was sent to me by a fan of the channel, so big thanks to him for providing the card. It now lives on in my, well, bits of it now live on in my Maximus 11 gene. I also salvaged all of the capacitors off that thing, and those are on some other random motherboard that I can't remember right now. And a motherboard that I haven't tested in a while. Like, I added the capacitors and haven't tested the board since. So it's just like, yeah. Anyway, I have plans for that board. It's just like, I have plans for so many things all of the time that, yeah. And it, like, you know what's really awful? X299 is coming, which I'm far more interested in than Threadripper 3. Threadripper 3 is coming, and yes, I'm going to be covering that. I'm actually going to have a Threadripper 3 CPU, which was recently confirmed to me. Like, originally, I was basically just planning to do some PCB breakdowns, and that was it. But no, I'm actually going to have a Threadripper 3 CPU, so that's great. So, yeah, I was hoping to kind of avoid Threadripper 3 and just go like, nah, don't have a chip. So, this is my excuse for not covering it that much. But yeah, that plan failed. Yeah. Anyway, so yeah, because I have too many things that I want to do because, like, the thing is, this is a massive time sink. Like, swapping out all of the inductors sucks to do. Because inductors soak up, as well, especially, like, this is a 6-layer PCB. This is not a, weak VRM by any stretch of the imagination. And so the power plane on this is very, very substantial. And so pulling inductors on a board like this absolutely sucks. And then installing new inductors, I'd argue, sucks more because, I don't trust myself to, like, hot air them onto the board without breaking the board. So yeah, I actually use soldering irons because I have 2 soldering irons, so I kind of tack down one side of the inductor, then do the other side of the inductor, then hit it from both sides. That kind of sinks it. Like, some of these are really nice. You can see which ones you can kind of see which ones I did first because those are the most out of alignment. Like this one right here, this one's awful. These 2 I think were the last ones I did, and those are by far the best in my opinion. But yeah, the soldering quality is atrocious because well, it's not yeah, it's pretty bad right there. But anyway, so why would you want to swap the inductors? So obviously with the Probinator, one thing I noticed is, like, the gene has quite a lot of overshoot. Like, relative to some other boards, there's quite a bit of overshoot on this board, and it's not really a big deal, but it was one of those things I was wondering about, like, because here's the thing, if you swap out the inductors for a lower inductance, you basically you store less energy in the inductors of the VRM, which means when you have a load release, you get less overshoot. At least on paper, you should get less overshoot. So that's why I swapped out all of the inductors. We went from the stock inductors that ASUS uses are 400 nanohenries each, which is really high, but if you consider how ASUS actually runs their VRM with, like, 2 power stages in parallel and then 2 inductors in parallel, that actually works out to a relatively normal inductance compared to most motherboards. So most motherboards from, like, MSI, Gigabyte, well, Gigabyte, for example, on their X570 boards uses 150 nanohenries per phase. So that's like less than half of what ASUS has per phase, per power stage, right? But ultimately, since these are in parallel, it does work out to be about 200 nanohenries. So, it's though the funny thing is, like, ASUS has been using these 400 nanohenry inductors on motherboards where they are actually 400 nanohenries per phase, which is really high. You know, most motherboard, like, well, if you go back in time, a lot of older motherboards would have really high inductance inductors, but it's that because they were running at like 200 kilohertz or 100 kilohertz VRM switching frequency. Modern VRMs, you can run 300, 400, 500 kilohertz, you know, with very little issues, especially with power stages. Like, you get power stages these days that are literally only spec'd at 500 kilohertz because it doesn't make sense to run them at anything lower. And it's just like, yeah, if you have parts like that, you can use significantly lower inductance inductors. But ASUS, for whatever reasons, likes to use pretty high inductance inductors. So, yeah, anyways, I was basically like, well, since there are 400 nanohenries to start with, and I have all of these inductors off of a Vega 56, which luckily, like, they're shorter than the ones from ASUS, right? Like, you can see the height difference there. You know, over here you can see the height difference, but they have the same footprint. So I was like, well, I have a bunch of these. Whereas if I wanted to do this on like a gigabyte motherboard, I don't think I actually have the correct inductor to do that. So I wouldn't do this on a gigabyte board because it's like I'd actually have to go out of my way to like buy inductors, and it's just like, yeah, I don't want to deal with that. But I have a bunch of these spare, so it was like, let's swap them. Let's swap them all on the gene. Yeah, so we went from the 400 nanohenries down to 190 nanohenries, which I was hoping to kind of improve the overshoot. I did manage that, but just not as much as I was hoping I would. So if we look at the actual results, here's the like. This is what am I doing? Oh, right, I'm on the wrong screen. Over here. So there, that's like the stock gene results, and yeah, I forgot to take measurements for the dye sense for some of those. Anyways, then we have the first revision, which this is like just inductor swap, the revision 0.1. So the inductor swapped version, you know, we have 10 millivolts less overshoot. Here, we, for some reason, like slightly more undershoot, but less overshoot again. Then we have slightly less overshoot and actually better minimums here. So level 8 LLC is just like, I don't like using level 8 LLC results because they're kind of a mess. Because at level 8 LLC, the VRM is really struggling to do what you're asking because... well, let's put it this way. The various like transient response optimization techniques for voltage controllers rely on a change in voltage. So the voltage has to drop a little bit before the controller can really do anything about it. And so telling the controller, hey, don't let the voltage drop at all, yeah, that doesn't tend to make the controller very happy because it's like it can't actually do that. Like, it literally can't do that. Like, the voltage has to drop because that's how the controller knows, hey, there's a transient. We need to do something about it. Anyway, so level 8 just kind of spits out some kind of weird results sometimes, but, you know, small reductions in overshoot. Level 7, we can much more clearly see improvements where it's like, okay, 10 millivolts less overshoot there, 20 millivolts less overshoot here, then 10 millivolts less overshoot there. So, you know, across the board, small overshoot reductions. At idle, there's really no improvement whatsoever, which I assume is just like at idle, there's no current really flowing through the VRM. So yeah, it's not going to make a difference. But at idle, we do see a small improvement in minimums, which is kind of like, okay, neat. That's nice. Not very useful because, again, it's idle. So who cares about idle performance? But there are some minor improvements in minimums like at level 7 as well. But level 6 LLC, yeah, no improvement in minimums whatsoever. And again, we see some minor improvements in overshoot. So, you know, 1.52 volts instead of 1.54, 1.51. So there we don't see an improvement at all. Like, this is the thing. At the lower LLC levels, the VRM is actually like the less LLC you have, or the more load, like the more V droop you have, the easier the easier it is for the VRM to maintain regulation. So like overshoot becomes less and less of an issue, and undershoot becomes less and less of an issue. So yeah, if you just like at the really high LLC levels, it just doesn't make a difference really, right? Like level 4 versus level 4, just literally straight up no difference. 1.41 versus 1.41. Though I do have a small improvement in minimums there, so that's kind of nice. So, you know, very minor improvements. The thing is also keep in mind that the oscilloscope is rounding to the nearest 10 millivolts. So if there's a 2 millivolt difference can actually change the average to the nearest 10, right? So it's like if it was previously, if it was averaging 1.254, that would round down to 1.25. If it's now averaging 1.256, that rounds up, or 1.255, it rounds up to 1.26. So, it's like a 10 millivolt improvement. It's like, well, that's not really a significant improvement whatsoever. Steady state, actually, I think, yeah, steady state saw some of the biggest gains where it's like, okay, 1.5, 1.52 versus 1.53. And then, of course, at the lower LLC levels, it just doesn't make a difference anymore. Actually, somehow, level 4, again, that's like 1.38 versus 1.3, well, 1.39 versus 1.38. 124 versus 127. I'm gonna say that right there is very probably the result of the rounding, as I said earlier. So it's probably just a rounding difference there. But anyway, so that's kind of the inductor swap. So that didn't really do as much as I was hoping for. So the next step was obviously more capacitors, right? Because we all know, just like if you like overshoot, yeah, if you have energy stored in the inductors and it's got nowhere to go, just add more capacitors, and that cleans up the overshoot. In theory, it would also improve our undershoot, because when the CPU suddenly starts pulling a bunch of current, it can pull that current from the extra capacitors instead of, well, it won't get it from the inductors until the high side MOSFET turns on. Because that's the whole issue, is just like, if the CPU starts pulling a bunch of current and the high side MOSFETs on any of the phases, like, here's the thing, if you have a 5-phase, there is a very good chance that at any given point in time, like that, there's a really good chance that if you're outputting, say, 1.5 volts to the power plane, one of your you're not going to have any phases turned on when a transient occurs. So then it's basically a race against how quickly can the controller tell some of the high side MOSFETs to turn on before the voltage drops too far. Now, if you just have more capacitance or faster, well, yeah, more capacitance closer to the load, with less ESR, less ESL, then the voltage will drop slower, and you have more time to respond to the sudden drop in voltage, because ultimately, the voltage is going to be dropping a bit slower. So yeah, and to that extent, that was this round of like multi-layer ceramics right here, right? That's like revision 0.2 right there, is those multi-layer ceramics, and also all of these extra aluminum polymers on the back. So these are, of course, these are 560 microfarads each. They're Nichicon RS8 series capacitors. So the RS8 series is low ESL optimized. It also has a low ESR, so these are like 7 milliohm ESR per capacitor. You can go lower, you can get 5 milliohm ESR, but they're also low ESL, which I can't remember the spec for the ESL compared to the the thing is, they don't give you a spec for the non-ESL optimized capacitors, so it's just like, well, don't actually know how much of an improvement that is, but these are relatively cheap, so I don't actually it's like, and they are still 7 milliohms ESR, so it's not like I'm sacrificing a ton of ESR for the, optimized for ESL branding that they come with. I assume there's a difference. It's just like they don't specify how big of a difference it is. So anyway, so I added all of these, and that was revision 2.0. Revision 2.0 basically did what I was kind of hoping for. 0.2, not 2.0, because it's not a final revision. Like, there's a good chance I'm going to have a revision 0.4 if I get bored enough and decide, because the thing is Buildzoid is bored. What can I do? Oh, I don't know. I'll just add more capacitors to some random GPU or motherboard and then test it and see if it made an improvement. There, boredom eliminated. Anyway, so that's revision 0.2. Revision 0.2 has less overshoot. Yay! Of course there's less overshoot. We have a bunch of extra capacitance. Not a significant difference on steady state for whatever reason. But yeah, in the really 128K prime 95, right? The really noisy test. There we see slightly less overshoot by another 10 millivolts. So at this point, I would say, okay, we've actually, this is a measurable improvement, because that is not just going to be a 2 millivolt rounding difference. That's a 10 millivolt, it's like an 11 millivolt rounding difference at the very least. So, that's actually a significant improvement. Hooray for me. Similarly, but we're still at like 1.55 there, 1.51. So small improvement here. So okay, that's a significant improvement over level 6 on the stock configuration of the motherboard. 1.45 here, which is still 1.45 at level 5, just because level 5 LLC is basically where the VRM is like level 5 is where the VRM is happy, right? Which is also like the minimums don't improve, but the minimums actually improved for level 7. Yeah, level 8, slight improvement in minimums. Big improvement over here compared to the revision 0.1. So yeah, level 8 LLC is just a bit strange. Also, the peak to peak at this point is actually pretty small. Then level 7, we also have an improvement in minimums, which is actually significant compared to the stock version of the board, not really compared to revision 0.1. So yeah, but by level 6, no progress. That's the thing. Is just like as you crank up the V droop, the requirements for the VRM to maintain out, like the VRM just has less work to do. So it's struggling less hard against the laws of physics, and so any more capacitors just kind of stop making a difference. So like I was really hoping to make improvements at LLC levels that actually make sense to use. Level 5, level 6, level 4. And yeah, I'm not making any real progress there. So that's kind of like, I'm very disappointed with that. So yeah, we have 1.37 here instead of 1.36. And then of course at level 5, it's just 1.3 versus 1.3. And actually, I don't even have an overshoot improvement there. So that really sucks. But hey, that did not stop me. The board obviously needs more capacitance, right? Like, evidently, not enough capacitors. If we're not seeing improvements, just keep adding capacitors. And that's why we have all these extra ones in the actual socket, because it turns out, like, ASUS doesn't fully populate their sockets on this board. And it makes sense why they don't bother fully populating the socket, because my version of the socket is actually, like, I have more capacity, like, I've added capacitors in places where they don't even have footprints for capacitors. Yeah, like it still doesn't make a very significant difference. So it makes sense that ASUS at the fact, like in the design stage, ASUS was like, well, those capacitors don't actually make a difference in terms of overclocking capability. So why would we pay for them? They don't do anything. But that's this one, like this cap right here. Then there's some really small ones as well. So like this right here, that's a 4.7 microfarad, 0402 multi-layer ceramic. Then we have these, this group of capacitors right here, that's all new. These two are new. These two over here, that's new. This one over here, that's new. These two over here, those are 22s. So the 0603s are 22s, the 0805s are 47 microfarads, and the 0402s are 4.7 microfarads. So I added 4 extra 0402s. I think the reason why the socket on its own doesn't come with any 0402s is there's a very good chance that any of the CPU socket impedance is so high that a capacitor in an 0402 package just doesn't make any sense. So yeah, there's like a good chance like adding these is the extra capacitance they add might actually make a difference, but the fact that they're in an 0402 package doesn't actually matter very much. Though it is worth noting that you can stack 0402s on top of a 0603 and it'll still clear these braces right here. So these braces you have right here, it'll still clear them if you put a 0402 on top of like this capacitor, which I realized while modding another motherboard. So it's just like there's a good chance I'm going to end up adding a bunch more 0402s. The other thing that it makes me wonder about is sort of like, well, actually looking at the Gene, I think this has far more power plane stitching than one of the other boards I'm working on, which is another thing. The thing is like I do really wonder about the design of the power plane itself should actually make a pretty significant difference to the transient response, because basically, if you have a 5 milliohm ESR capacitor, but then your whole power plane has another, 1 milliohm of resistance, yeah, your power plane is like making your capacitor like 20% worse, 20% worse, right? Zoom out a bit there. So that's one thing. And the Gene actually, like, you can see a lot of vias in the power plane right here, and of course right here, which is right along the, where the inductors connect. And this right here, I don't know, there's nothing there, right? Oh no, I guess, yeah, okay. But yeah, so this has a lot of power plane stitching. Unfortunately, it's not quite as easy to see the power plane stitching on some of the other boards. And obviously you want it done as near to the capacitors as possible and that kind of thing. And then of course a lot of it's in the socket itself. But yeah, so I added a bunch of extra multi-layer ceramics, and there's also the multi-layer ceramics I added to the actual, like the aluminum polymers. So there's two 22s over here, there's a 47 over there, and there's another 22 over here. I really wish I had like mounting points for those like right up against the socket. You know, maybe more of this up against the socket up here. All of this over here is actually for the GPU. Like all of these multi-layer ceramics up here. Well, not showing you that. Yeah, all of this, that's actually for the iGPU. This cap right here is vCore, but all of the multi-layer ceramics and all of these bulk capacitors, that's actually iGPU, which is just like, well, yeah. Which actually one of the potential upgrades with the, like, say, the Z390 Godlike, and actually, I don't know how many boards MSI has where they literally, like, they don't have an iGPU rail. And the thing is, that can actually lead to an improvement in transient response, because instead of having a silly iGPU rail, going from like here to your socket into this area, you can actually just have like vCore power plane all the way from like depends how far you wrap the vCore around the socket, but like the vCore pins of the socket are like sort of in this area. Well, you can have a power plane that just kind of goes like that, and just connects sort of from more. You basically have a bigger cross section for the power plane connecting to the CPU socket, which can also lead to a transient response improvement because, yeah, you just have more cross-section to deliver your power with power to the CPU with. Anyway, so this was revision 0.3. This is revision 0.3 in its current form with all of the extra capacitors in the socket. And what did that do? What did that do to in terms of performance? Well, yeah, 0.3. So idiot me forgot to go from 800 kilohertz switching frequency, because I was doing some other testing where I was trying to see if 800 kilohertz actually makes a difference. It doesn't. Maybe at like idle it makes a bit of a difference, but it really doesn't make a difference when you're looking at like 128K, where it just like that's the CPU screaming gibberish at the VRM and the VRM kind of not knowing what to do about it. So improvements, I mean, even less overshoot. Yeah, that's exactly what I wanted. You know, that's totally what I was struggling with, having too much overshoot. That's yeah. I'm as you can probably tell, I'm actually really disappointed. I did actually improve minimums on level 6 a little bit, but again, keep in mind, rounding is like, you know, it could be just a rounding difference there. We're still the same at level 7 for undershoot. And then by level 5, it just doesn't make a difference. So level 5 is obviously the LLC where the gene is like happiest, and it's just like that seems to be where ASUS. That seems to be the LLC for which the VRM is like really optimized, like level 5. Level 4 you can make an argument for as well, but level like 6, 7, and 8 are just like 6 is still kind of viable because it's okay, you know, in say steady state loading, but in really inconsistent loads, level 6 just doesn't make any sense, and 7 and 8 are just like, you shouldn't use 7 and 8. Maybe if you had like the thing to keep in mind with the LLC levels is if you actually have a lower core count CPU, your transients are going to be much smaller. So if you're on like a quad core, level 7 would actually probably give you perfectly good voltage regulation. Like if you're on a quad core with no hyperthreading, yeah, it would actually potentially make a lot of sense. Whereas if you're on like a 6 core with hyperthreading or an 8 core with hyperthreading, then it's just like, well, more droop is better. Also, one thing that this makes me want, like, the other thing is if I was testing a higher current draw CPU, we might actually be seeing better, bigger improvements from the extra capacitors I'm adding, because obviously there's just more like the CPU is going to grab more current on a load start, or like, yeah, load start or a load release. And that's going to make more of a difference. Well, load release is going to have more current flowing through the inductors, which causes more overshoot. So that's where well, the thing is, I don't care about the overshoot. Like, that doesn't translate into better overclocking range. That's just like, there's maybe slightly less chance that you'll kill the CPU if you're trying to push 2 volts into it on liquid nitrogen or something, which I guess might be beneficial, but yeah, no, like, it's not a priority. Like, I want better minimums. I've kind of done that, but only at LLC levels that are just completely useless in the first place. So, yeah, not really. I'm not very happy with the results. Anyway, other than that, let's look at voltage matching. So, here, all of the boards are trying to hit 1.3 volts. And unfortunately, I only started doing this testing after I already modified the gene a little bit. So we don't actually have results for a stock gene, but as you can see, like, By the time you get to level 5 LLC, the stock gene performs basically exactly the same as my heavily modified gene, except maybe overshoot, right? Like, let's see, level 5, 1.4, nope, even overshoot. Even overshoot is the same, except maybe like steady state overshoot improves by 10 millivolts. Yay! Look at that improvement. Though my idle peak to peak looks great. You gotta give me credit there. I guess my board might be slightly better at making like CPU-Z screenshots. Right, like if you want to take a screenshot of CPU-Z, my board might have like a 10 millivolt advantage over a stock gene, which is just like, yeah, that's not significant. Like that nobody cares. I don't care. Like, I'm disappointed with the results. But hey, I mean, on the other hand, this is like the gene is a high-end Z390 motherboard meant for overclocking. So it's like if me haphazardly slapping extra capacitors on made a significant difference, that would actually be kind of concerning, wouldn't it? Yeah, though there's also a chance that at this point, maybe I should just look into reprogramming the firmware of the voltage controller. The thing is, that is outside of my area of current understanding. It is something I definitely want to, well, I want to get good, like, I want to be able to do that, but as of right now, yeah, not able to do that without, well, I'm very worried that I'd blow up the CPU, is basically what I'm getting at. Because you could, like, I could potentially really screw things up with that. So, yeah, but I do want to try reprogramming the controller, because at this point there's a chance that I might be able to tweak some of the transient response optimizations of the controller to be more aggressive. And because now the VRM has a lot more bulk capacitance on it and just capacitance in general and more current slew rate. So it's like, well, you know, like ASUS had the controller firmware tuned for their configuration of inductors and capacitors, and evidently it works well enough that the board doesn't kill my CPUs with what I've done to it. But that doesn't necessarily mean it's like that I'm getting peak performance out of it at this point, right? Like I could probably, like, I should look into retuning it for better, yeah, to be better. But I'm not sure what I'd actually have to do that. Because that is, as I said, like that's outside of my current area. Yeah, that's just outside of my understanding right now. So got a lot of reading ahead of me to get that, like, to try make improvements to the actual firmware, because yeah, that stuff's really complicated. Like that's where all of the difficult math engineering stuff comes in. It's just like, and that's it's all, yeah, can't deal with that. Anyway, let's talk about the voltage matching results. Where was I? Right. So voltage matching. So level 8 LLC on the gene actually does have a little bit of voltage boost. Like always, as you can clearly see, the DiSense is reporting 15 millivolts more than I'm actually setting. So yeah, it's I think they're applying an offset. Like I straight up think ASUS is just applying an offset, because even at idle, it is just like idling is way, like idle is off by 20 millivolts. Right, according to the oscilloscope. And the thing is that idle, this voltage reading should be far more accurate, like should get steadily more accurate. And it just looks like across the board from like level 6, no, it's like from level 6 LLC up, it basically looks like the board applies like a plus 20 millivolt offset, and it's just like, well, runs with it. Anyway, so on the inductor swapped version of the board, yeah, I made actually a small improvement. Again, at level 8 LLC, look, I made an improvement in the undershoot and an improvement in the overshoot, right? 1.46, 1.47. Same, like, basically across the board, minor improvements at level 8 LLC. But again, like, you shouldn't be using level 8 LLC in the first place because it's just universally bad. So, useless improvements. Totally pointless and waste of my time. Idle looks great, though. Idle looks amazing, except again, nobody cares about idle anyway, and it's mostly just overshoot improvements. So then we go up to level 7, where, you know, it's 1.32 volt set voltage. We actually get about 1.3 onto the DiSense, 1.36. So I think the thing is the DiSense isn't super accurate because that's the Super IO reading. So the Super IO rounds, I think, to nearest 12 millivolts. So yeah, it's awful. Or is it nearest 12? It might be near. Wait. That's a 9 millivolt difference there. So it might be nearest 9 millivolts. So yeah, it's not super accurate, which kind of sucks. But anyway, small improvement in minimums again, small improvement in overshoot. For level 7 LLC, 800 kilohertz doesn't make a difference. If anything, it seems to make the peak to peak slightly worse, which is more noticeable over here. But yeah, like you can see that no difference, right? This is just 500 kilohertz auto VRM control settings. This is 800 kilohertz extreme settings, and it's just like yeah, it doesn't do anything, which like again sort of matches, you know, I guess a lot of people's experience where it's just like you can crank up the VRM switching frequency and a lot of the time it just doesn't make a difference. Well, yeah, you can measure that it doesn't make a difference. I'm glad that the measurements confirm, you know, my experience where it's like, yeah, you can try crank up the switching frequency, it doesn't make a difference. Which kind of, that's like, well, I guess the thing is like if it actually did make a difference, why wouldn't they just ship the board at a higher switching frequency in the first place, right? Yeah, it does make your VRM efficiency worse, but come on, like it's not like this board exactly has a. This uses 60 amp power stages from International Rectifier. This really doesn't have a thermal problem. So it's just like sacrificing a bit of thermals for overclocking range is like that's a trade I wouldn't be surprised if they did at the factory if it was a trade that they could do, right? Like, but no, it isn't because you know progress. So anyway, yeah, so across the board, you know, and then like here it doesn't actually make a difference at 192k. That's yeah, that's 192k prime 95 over there. So right, like that column right here. So yeah, mostly just overshoot improvements, right? Because like here we're doing 1.43 across the board, and there it's like 1.45, up to 1.46. Whereas level 6 is actually the 1.44 on this version of the board. But at level 6, like yeah, level 6, I still don't have better minimums. Nah. Even at like the 128k test, the minimums aren't better. So yeah, it's just like even in the voltage match testing, you can clearly see that it's just like at level 8 LLC, level 7 LLC, there's some minor improvements. But once you're down to like LLCs that you would actually be reasonably using, like 6, 5, 4, or really just 5 and 4, because level 6 already isn't really ideal, right? Because you have worse steady state. Yeah, which actually, yeah, level 6, again, picks up a little bit of minimum on steady state loading. But again, like it's worse than level 5, so why would you run it? And level 5 is like 1.33, 1.33, 1.31 versus 1.31. 1.49, right? The overshoot reduction is real. Yep, that's there. So that's 1.48 versus 1.49 right there. And it's just like, okay, well, there's a reason why the gene ships in the configuration it ships in, right? Like there's a reason why the CPU socket does, like, actually, better example would be to just open it up. Because even on the front of the board, see all of this? See all that? Well, actually, I think, no, those are empty pads over there. But also over here, we have empty pads, and it's just like, yeah. So that's why those pads are empty, is like it doesn't bloody make a difference. Right? Your minimums, no matter what I do, the minimums just refuse to change at LLC levels you should actually be running. Now, some people might be like, oh, ASUS doesn't optimize for level 8 LLC. You shouldn't use level 8 LLC. Like, really, you should straight up not use it level 8 LLC. What I find kind of funny throughout the probinator testing is that actually, if you look at like ASRock boards, their level 1 LLC is like, I think, equivalent to like level 6 ASUS. It's like their most aggressive LLC setting is still quite droopy. And that is true for a lot of, like, quite a few motherboards where it's just like, yeah, you can't actually set a flat load line because they won't let you, because it's a dumb idea. And they'll put a graph in the BIOS where it's like that looks like you set a flat load line, but that's reflecting the super IO readings from the socket, not the actual voltage readings that the controller sees, because the controller, this lovely chip right here on the gene, yeah, that sees the die sense voltage from the actual VCC pins of the CPU socket. So, well, the voltage monitoring pins from the CPU that Intel provides, so that VRMs can have an accurate load line. And yeah, so anyway, yeah, there's a reason why there's no point, why genes ship in the configuration that they ship in. It's just like, because it's optimal. Like, straight up, it's optimal for the LLC settings that you would actually want to run on this board. Now, admittedly, on some other boards, you could run, like, I think, like, the Dark, I think you can technically run, like, the level 6 equivalent LLC. and still get basically similar performance to what, like, well, better. Like, the thing is, it just means you have less idle voltage, which is just like, okay, well, does that actually matter that much? Not really. Um, but yeah, that's the thing. It's just like, so, you know, modding the gene, definitely not worth it. I have some other boards that I am modifying, but the thing is, it's also like, I should be modifying more. Like, arguably, I'd see better results trying to modify a motherboard that's really, like, more low-end, but at the same time, it's just like, on low-end motherboards, I'm not so much concerned about the transient responses. I'm just concerned about, like, the VRMs just running are gonna run stupid hot because the MOSFETs suck, or whatever power stages they have suck, or whatever power, or however, like, or, you know, like, the funny thing is you can have nice power stages, but just not have enough of them, and then the VRM runs really hot, or like that kind of thing. So it's just like, yeah, if you have a low end board, like the voltage regulation being crap, that's just kind of an irrelevant issue because the VRM is going to overheat before that becomes a problem, like before that becomes a serious concern. So yeah, anyway, so this is the modified gene. I am still going to modify other boards just because I'm interested to see if there's any board where it would actually make sense to do this, right? And so yeah, I'm working on the Z390 Aorus Master. I have a bunch of modifications, but yeah, this is the current state of the gene. And for now, I think like I don't think I'm gonna push this any further because I don't think there's like it doesn't make sense at this point. Like it's not gonna go anywhere, right? I'm pretty sure. Like yeah, I guess I could. Well, yeah, no, I can't see any further improvements I can make. Also, the multi-layer ceramics I like using, they're relatively expensive, so I don't want to dump them all on one motherboard because it's like, yeah, I don't really want to be buying a bunch of them. Like the 47s, like the 47 microfarad caps, like they're pretty expensive. If you're buying them in like yeah, like it just yeah. So it costs money to do this. So I don't really want to go and just burn all of my capacitor, like because the thing is desoldering them really sucks. Um, Desoldering multi-layer ceramics is something I really don't trust myself with. So, well, to like maintain the capacitor in like good health, because they are relative, like they're sensitive to thermal shock, which already just the way I solder these on is like, yeah, this is not a good way. Like reliability is a real concern with my soldering for multi-layer ceramics especially. But it's just like, yeah, if I desolder them, then I'm like 99% certain that I've roasted them, so I don't really want to go and like use them on another board at that point. So yeah, because of that, it's just like I think I'm gonna like leave the gene alone at this point because it really I like it's not making any, I'm not making any improvements, and it is a, well, it's also a time sink, right? Not just a money sink. It's like, yeah, the capacitors cost money and then it takes time to add them. And, well, I'm not making any improvements, so may as well stop at this point. But I do obviously have a bunch of other boards that I want to work on. So, like, the Z390 Aorus Master is currently the one that I'm messing around with. That's on revision 0.2 at this point. Unfortunately, like, that board is one where I'm, like, actually really hoping that I could maybe make a difference in the minimums, but because the minimums on it kind of suck, in my opinion. But, at the same time, it's like I kind of think it might be a power plane problem there. Like there might not be that much I can actually do, except maybe like, or I have to like cram everything in the socket because looking at the, like the bulk capacitor, the way the bulk capacitors connect to the power plane just isn't exactly confidence inspiring in my opinion. So, yeah, but we'll see how that works out. Damn it, what? Oh. And I just dropped that one. Found it. So, yeah, no, basically, like, yeah, I think the Gene actually just has way more stitching in its power plane. And they're both 6-layer boards, so that is, you know, not exactly confidence inspiring. But this is the thing. This is the kind of stuff, like, where it's like, you can't eyeball this, which is really annoying. It's like you can eyeball if the VRM will have thermal issues with just like, are the MOSFETs any good? And is there enough of them? And if there's, you know, if you answer yes to that question, then it's like, yeah, it's probably not going to have thermal problems unless they really screwed up the heatsink design. But then there's, of course, the whole... well, then you get to things like transient response and voltage regulation, and it's just like, too many variables. Way too many variables, because it's just like, what do you do with the capacitors in the socket? What do you do for your bulk capacitors? How is the power plane laid out? How is the power plane connected to everything? And yeah, that just makes that kind of impossible to tell for sure. There we go. Just going to check that. Well, actually, you can't really check that. It doesn't shorten them. Nope, can't. Well, it looks fine. So, yeah. That's it for this video. Oh, damn, this is 40 minutes long. I guess I didn't need to include the sort of outro with reassembling the gene. But anyway, hopefully this was somewhat interesting. Or it probably wasn't, but hey, I don't know. But yeah, this is just like, yeah, so there's definitely no point trying to modify the gene. Unless you also know maybe how to reprogram the firmware. And you're like good at that. Which, well, I know how to reprogram the firmware. I'm just concerned I'm going to do it wrong. So that's kind of the issue. So yeah, anyway, yeah, modding the gene, totally not worth it. Which, I mean, how surprising, right? Like, it's a high-end board. If it was worth it, that'd be concerning. Anyway, yeah, that's it for the video. So thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. Also, big thank you to whoever it is that actually sponsored this motherboard to me. It's not ASUS. It's like one of the fans of the channel bought this thing for me, but I can't remember who it was at this point. But hopefully, you know, the adventures of the gene so far have been entertaining for you. I actually do want to do some memory. Well, no, I need to move on to other boards. So I'm probably not, well... I really like this isn't well this board me and this board's BIOS do not get along, but at the same time it's like it's a real shame that this board spends so much time just sitting in its box, right? Where it's like I really wish I used it more is kind of what I'm getting at. So anyway, yeah, but that's it. So anyway, well, yeah, so thanks to whoever it is that, you know, funded the board. I hopefully, like, he should know who he is. So yeah, and I do apologize for not remembering who it was, but it's just like, yeah, but kind of hard to keep track of that kind of thing for me. Don't really make it a priority. So yeah, but I'm still very grateful that I got the board, right? It's just like, because without it, like this, like I wouldn't be able to do these videos at all. So, what else was there? Right, if you'd like to support me, and what I do here with actually hardcore overclocking, I have a Patreon where you can support me directly, or if you don't like Patreon, there's the AHOC Teespring store where you can buy shirts, stickers, posters, hoodies, that kind of thing. You can find a link to both of those down in the description below. Yeah, those help out immensely with running the channel because, well, they allow me to do silly things like this, as well as silly things like, you know, assembling building the probinator like that. So yeah, that's it for the video. Thanks for watching, and goodbye.